So, hello everyone, welcome back to the second week of NPTEL lecture series on cycloaddition. So, in the last week we talked about 4+2 cycloaddition reactions, and in that mostly we talked about intermolecular Diels-Alder reaction. That means you take separately diene and dienophile and then heat it to get a monocyclic compound. So, we also discussed about normal 4+2 cycloaddition reaction and abnormal, that is inverse electron demand Diels-Alder reaction. In addition, we also talked about hetero Diels-Alder reaction, where one of the atoms in either diene or dienophile, or in some cases both diene and dienophile have been replaced by a heteroatom. Okay. So, today what we will do, we will talk about intramolecular Diels-Alder reaction. That means you have the diene and dienophile in the same system, or in other words, the dienophile is attached to the diene. In a normal intermolecular Diels-Alder reaction, what you get is a cyclohexene ring, only one ring you get. But in the case of intramolecular Diels-Alder reaction, you will get more than one ring. So, that is the major advantage of intramolecular Diels-Alder reaction. So, when you talk about intramolecular Diels-Alder reaction, there are two types of intramolecular Diels-Alder reaction. In short, intramolecular Diels-Alder reaction is often written as IMDA, intramolecular Diels-Alder reaction. And as I said, there are two types. The first one is type 1. What does type 1 mean? So, here you have the dienophile. So, assume that this is the dienophile and this is the diene. Now, this dienophile is attached to carbon number 1 of the diene. Okay. If the intramolecular Diels-Alder reaction takes place in such system where the dienophile is connected to carbon number 1 of the diene, then this type of intramolecular Diels-Alder reactions are called type 1 intramolecular Diels-Alder reaction. Obviously, when this undergoes intramolecular Diels-Alder reaction, what you get is a fused bicyclic system. Okay? So, type 1 IMDA will give fused bicyclic system. Okay? This is rule number 1. Now, what is type 2? Okay? Here, as you have seen, the dienophile is attached to carbon number 1. In type 2 IMDA, the dienophile is attached to carbon number 2. Okay. So, now if this undergoes intramolecular Diels-Alder reaction, then you will not get fused bicyclic system. Okay. Most of the times what you get is a bridged bicyclic system. You can see this is the bridged bicyclic system. Okay. So, these type of reactions are called type 2 IMDA. Okay. And more importantly, in order for IMDA type 2 to happen, the minimum ring size of the second ring other than the cyclohexene ring should be 7-membered. At least it should be 7-membered, then only type 2 IMDA will happen. Okay. So, with this basic introduction, now we will move to select examples of type 1 intramolecular Diels-Alder reactions today. So, there are many examples, we will go one by one. So, look at this example. You have a diene and the dienophile is alpha beta unsaturated ketone, and that is connected to the terminal carbon. It should be either connected to terminal carbon or the internal carbon. If it is connected to terminal carbon, then it is type 1 IMDA. So, this gives the cis-decaylate system. Okay. So, how does it happen? Okay. So, when you draw a transient state, so you take this diene here and the dienophile, and the carbonyl group of the dienophile is in the endo transition state mode. That means the carbonyl group is under the plane of the diene. Okay, only in this transition state it is possible. If this happens, what you will get is the cis ring junction. Okay, now you have two changes. One, the methyl group has moved by one carbon. Two, there is no electron withdrawing group attached to the dienophile. If you heat it, then you can see the ring junction, it is trans-isomer. Okay. So the major difference you will see here is the absence of the carbonyl group. Okay, that means the HOMO-LUMO energy gap is high. So in order for this intramolecular Diels-Alder reaction to happen, you have to heat it at very high temperature. And if you look at the transition state, it goes via exo transition state, and also you can see that there is a 6-membered, and since the carbonyl group is not there, the thermodynamically more stable exo transition state will lead to the trans isomer. Okay. The presence of the carbonyl group, which we have already discussed in details, that gives the secondary orbital overlapping. Because of that, the kinetic endo product is formed in Diels-Alder reaction. When the carbonyl group is not there, or when the electron withdrawing group is not there, then there is no such secondary orbital overlap, and that leads to the more stable thermodynamic exo product. But only difference is you need to heat it more to get exclusively or predominantly the exo isomer. Now let us look at a few more examples of type 1 intramolecular Diels-Alder reaction, and let us see this particular example. So here when you have a closer look at this molecule, you will see there are two dienes. So this is diene number 1 and this is diene number 2, and from the normal intramolecular Diels-Alder reaction point of view, this can be a better diene than this one. But if you use this as diene, where is the dienophile? The dienophile could be either this double bond or this double bond. But one will give 4-membered ring, the other one will give 7-membered ring. So what they have done is, if you take this tetraene and then treat with potassium fluoride, or any fluoride is well known for removing silyl group. Okay, once this triethyl silyl group is removed, that will give you enol, and enol is nothing but the corresponding ketone. So now when you look at this intermediate, you can clearly see this is the diene which will undergo Diels-Alder reaction, and this is the double bond which will act as a dienophile. So that will give you the corresponding bicyclic compound, and that is the corresponding endoadduct, and also the Decalin system you see cis compound. So that is because the carbonyl group comes from the same side as that of on the diene. Now let us look at the next example. Here can you see a diene? In this example you cannot see the diene obviously, but if you have a closer look at this particular substructure, you will see that this is nothing but cyclobutene. So when you have cyclobutene, this cyclobutene is known to undergo electrocyclic ring opening. When this electrocyclic ring opening takes place under thermal condition, you get this tetraene. So now when you look at this tetraene, you have diene number 1 and you have diene number 2. Okay. So this is diene number 1 and this is diene number 2. So that means in principle there are two dienes which can undergo intramolecular Diels-Alder reaction with this double bond. But we know that the diene 1 is the one which will undergo intramolecular Diels-Alder reaction, because once it undergoes intramolecular Diels-Alder reaction, so what you get is a cyclohexene, okay, and the double bond which is formed as a result of this intramolecular cycloaddition is part of the aromatic ring, or in other words, during this electrocyclic ring opening, the de-aromatization took place. Okay. So, now after the intramolecular Diels-Alder reaction, the aromaticity is regained. So, that is why the diene 1 will undergo intramolecular Diels-Alder reaction and not the diene 2. So, let us move to one more example. So, in this particular case, what you see is, unlike the previous example where you had a carbonyl group at this position, now you do not have a carbonyl group. Okay. So, that means you have to heat it at high temperature. Yes, it has been heated at 160 degree, and what you get here is exclusively the trans isomer and not the cis isomer. Why? So, already we discussed about this, why you get trans isomer if there is no electron withdrawing group attached to the dienophile. So, now if you look at these two transition states, in the trans product transition state, you can see a very nice chair like conformation, whereas in the cis transition state, you will see a steric repulsion between this methyl group and then this CH2. So, that is why always in such cases you get the trans product. So, this is what we have seen in the earlier example also, where the benzocyclobutene underwent ring opening via electrocyclic ring opening followed by intramolecular Diels-Alder reaction, you got a trans product. Likewise, here also you will get exclusively the trans product. So, now let us have a closer look at this type 1 IMDA. So, if we have a substituent at either diene or dienophile, what will be the effect of such substituents? So, when this bicyclic compound is formed, you get two new sigma bonds. One is the internal bond, the other is peripheral bond. The peripheral bond is formed between the terminal carbon of the dienophile and the terminal carbon of the diene, whereas the internal bond is formed between the internal carbon of the dienophile and internal carbon of the diene. Okay. So, now let us take one example where you have a substituent on the dienophile. Earlier we have seen the substituent, that is electron withdrawing group, is part of the second ring, okay, the carbonyl groups here. So, that is part of the second ring. So, now we have a substituent which is at the terminal carbon of the dienophile. That means in the product it will be part of the cyclohexene ring. So, you can see here in this case what you get is 1,3 isomer. What you get is 1,3 isomer. Okay. And normally 1,3 isomer is not allowed, but because of here the position of the ester, you get 1,3 isomer, and that also will give you the endo product, because endo product is with respect to the ester. Okay. The ester can go easily below the diene, so it can give endo product, and more importantly it is stereospecific, because whatever stereochemistry you have it on the dienophile, that is the double bond, that will be retained in the products. Okay. And likewise, this type of tetraene already we discussed how one can generate. You can generate from the corresponding benzocyclobutene, and then when you heat it, this can undergo type 1 IMDA to give this trans-decalene system. So far, whatever we have discussed on type 1 IMDA, the starting material is achiral. You have a chiral center adjacent to the diene. Whether this will have any effect in the Diels-Alder reaction. So, in order to make this Diels-Alder reaction to work, first you have to oxidize this allylic alcohol. So, that is done with the chromic acid. So, when you do that, automatically this undergoes Diels-Alder reaction. It is type 1 IMDA to give mixture of these two endo products. In that, this particular isomer is the major product. Okay, you can see both are cis, but this is the major product. Why? There is a preference. So if you look at the transition state, you have to account the bulky isopropyl group. So in this particular transition state, if you have a closer look at, you will see that isopropyl group in equatorial position, whereas here the isopropyl group is in axial position. So that will lead to 1,3-diaxial interaction. Okay, so that is the reason why this particular cis product is the major product. So, or in other words, the substituent attached in the tether, this is called tether, that is a linker. The substituent attached in the linker can decide the outcome of type 1 intramolecular Diels-Alder reaction. Again, this is another example. You can see there are two substituents, okay, chiral substituent, and that will force the diene to properly go under the dienophile. And more importantly, if you look at this carbonyl group, it is outside the ring. It is not inside the second ring, it is outside the ring. So when you do this, then you will get trans isomer. Okay, this you can easily draw. You take this diene and then put the dienophile under this. The carbonyl group will be under the diene. So you will get the trans ring junction. Okay, don't get confused. I am giving exactly opposite example. Here in this case there is no electron withdrawing group. Okay, so now if you heat it, then you can draw a transition state like this. In this transition state, what you get is the exo product. Okay, what you get is the exo product because there is no electron withdrawing group. Okay, I already mentioned in the second slide, when you have electron withdrawing group, then it goes to endo. When you have no electron withdrawing group in the dienophile, it gives exo, but you have to heat it at very high temperature. So this is the transition state, and that will give you the trans AB junction of a steroid skeleton. Let us go to a few more examples. So again, now the tether has a 5-membered ring. Okay, like the previous example, now the tether has a 5-membered ring. So now if you do an intramolecular type 1 Diels-Alder reaction, then there are two possibilities. One, of course, the endo process, another one is the exo process. So that is because this CC bond can rotate. This CC bond can rotate. So you can see here this CC bond, if you rotate, you will get this conformer. Here the oxygen is in the top, whereas here the oxygen is in the bottom. Okay. But if you look at these two conformers, this carbonyl group of the dienophile is below the diene. Okay, that means this is endo product. Whereas here this carbonyl group is away from the diene. That means this will lead to exo product. Okay. So upon heating, you get this as the major product. Okay. So this is endo product and this is exo product. Okay. So at room temperature, that is at lower temperature, as you know, at lower temperature the kinetic endo product will be formed in higher quantity. So that is what happens. At room temperature the endo product is formed in 8:1 ratio with respect to the exo product. Whereas if you heat it, the thermodynamic product, that is the exo product, is formed in higher quantity than the endo product. Okay. Let us continue some more with some more substituents on the dienophile. So now if you look at this, you have one substituent on the diene and you have two substituents on the terminal carbon atom of the dienophile. So, this gives very interesting bicyclic system. Okay. So, as you know, this has electron withdrawing group. So, obviously one is expected to give cis product. And how is the transition state? So, you draw the transition state like this. First you take the diene, okay. This is the diene, okay. Up to here you draw, then the CH2O, carbonyl, and you draw in such a way that the carboxylic acid should be under the diene, then only you will get endo products. Okay. So, this transition state will give you this cis product. Okay. Again a similar reaction, but you have two alkyl groups. Okay. So, what does it do? The two alkyl groups. So, the two alkyl groups will force this substituent in such a way that again you will get the endo products. Okay. Again you will get the endo product. You can see the diene, and this dienophile will come in such a way that the ester will be under the diene, and now this double bond, okay, is beta gamma and saturated. So, this also in principle can migrate to more stable alpha beta unsaturated lactone. Okay. And instead of dialkyl, if we have diester, okay, and here instead of one methyl we have cyclohexene, again you get the same, okay, the endo product as the major product. Again one can see, so how this forces because of the Thorpe-Ingold effect. Okay. This is well known in the literature. So, now how about substituents in the diene? How about substituents at internal carbon? When you have such system, then the outcome will be different. Okay. So, you draw this transition state for both. Okay. This particular case, this is syn, or we call it as endo transition state, where you see the carbonyl group under the diene, whereas here this carbonyl group is away from the diene. But in this particular case, though the carbonyl group below the diene is normally favored at low temperature because of the secondary orbital overlap, now there is a strong steric repulsion between the oxygen and this hydrogen CH2. Okay. Because of that, it proceeds via this exo or anti-transition state. It leads to trans-Indian system. Now, if you have a chiral center adjacent to the dienophile, will it have any effect? Yes, it will have effect. So, what you should do, again you should draw a conformation like this, and if you look at this O-benzyl and this methyl group, I am sure you would have studied A13 strain, allelic 13 strain. So, that conformation should be in such a way that A13 strain is minimum. So, this is the only way you can keep the methyl and then O-benzyl group opposite to each other. In this conformation, if you look at this particular ester with respect to the diene, they are away. That means it is not under the diene or above the diene. So, that means it will lead to exo product. So, again you can see here it gives the trans products. Okay. So, this transition state is important, and sometimes the substituents on the diene or dienophile can significantly influence the outcome of the intramolecular Diels-Alder. Likewise, now the substituent, that is sulfone, is closer to the diene. The earlier case, the OBN was closer to the dienophile. Now it is closer to the diene. Again, you have to draw the conformation in such a way that allelic 13 strain is minimum. then this will lead to again the trans isomer. Okay. So there are many such examples. You can go through literature to find how the substituents closer to diene or closer to the dienophile, but in the tether affects the stereochemical outcome of the products in intramolecular Diels-Alder reaction type 1. In intramolecular Diels-Alder reaction, people also have used some removable tether groups. For example, one can have a silicon group. See, for example, you take this dienol and then treat with this type of silane chloride. Basically, what you are doing is you are protecting the alcohol as silyl ether. Okay. So that will undergo intramolecular Diels-Alder reaction. You can see this is how it will form. Okay. And this will undergo intramolecular Diels-Alder reaction, and that will give you this bicyclic compound. And as you know, this Si bond, C-Si bond can be easily oxidized using the Tamo-Fleming method. That is, you have to use a combination of fluoride and then peroxide. That way you will get the diol. Okay. So this is very easy method to make tetra-substituted cyclohexene with complete stereo control. One can also use magnesium. If you take this same alcohol and then treat with this vinyl magnesium bromide, so it can go through a similar diene formation with a magnesium dienophile. That means you will get like this. Okay. So this will undergo an intramolecular Diels-Alder reaction, and afterwards the OMG bond can be hydrolyzed and CMG bond will give the corresponding hydrogen. So what you are doing is you are fixing 3 stereo centers in this reaction. Okay. So this is again another example. So you will get depending on the nature of the methyl group. Here this is trans, this is cis. So accordingly you will see the stereochemical outcome of this compound. Okay. Actually, so this is wrong. The correct product is so this is the correct product. Only this stereo center changes. Okay. And one can also use boron as removable tether. So if you have an alcohol and this diene alcohol can replace one of the isopropoxy group of the boronate, so that will lead to the isopropyl Okay. So this will undergo an intramolecular type 1 Diels-Alder reaction, and followed by this boron can be oxidized and hydrolyzed to get the corresponding diol. Okay. So this is also quite easy using boron as a tether. One can do successfully intramolecular Diels-Alder reaction. So can we do intramolecular hetero-Diels-Alder reaction? So intramolecular hetero-Diels-Alder reaction, we have discussed quite a few examples. Is it possible to have a heteroatom in the diene or dienophile in intramolecular Diels-Alder reaction? Yes, it is known. See, for example, if you take this hydroxamic acid precursor, okay, this if you treat with oxidizing agents, so this NHOH can be oxidized to corresponding nitroso compound. So now you see this is acyl nitroso compound and can act as a dienophile, and we already have a diene. So this can undergo an intramolecular hetero-Diels-Alder reaction to form this bicyclic oxazinolactone. Okay, one can also cleave this NO bond later. So this has been successfully used in the synthesis of a natural product called lepidine. Then this compound is very easily made from cyclohexane 1,3-dione and from citronellal. Citronellal is commercially available, well-known monoterpene. Okay. Just to mix these two, it will undergo aldol reaction to get this compound. Now, if you look at this, this is a heterodiene and this is the dienophile. So, this can undergo an intramolecular Diels-Alder reaction, but intramolecular hetero-Diels-Alder reaction. And the way you have drawn the 6-membered ring, that is a chair-like transition state. So, that will lead to this entropy. And also the chiral center, that is with the methyl group, that helps in fixing the stereochemistry of these two newly formed stereocenters. Can you generate heterodienophile in situ? Yes. For example, if you take such system and then if you treat with base, it can undergo elimination of this acetic acid, or you can heat it. When you heat it, it can undergo elimination of acetic acid through cis elimination. So that will lead to this heterodienophile, which is in situ form, can undergo an intramolecular Diels-Alder reaction through a exotransition state to give this compound. And this can be further extrapolated to very interesting natural product like compound. So this is another classical example where the diene is already present and the dienophile also already present. The diene is a standard diene, whereas the dienophile is simple imine. Okay. So you draw the conformation in such a way, because this is alpha, so you draw the conformation like this, and now you have the imine, which is the dienophile, comes from the top. So that will lead to this very interesting tricyclic compound, and this is the key intermediate in the total synthesis of few alkaloids. Okay. So what we have discussed today is about intramolecular Diels-Alder reaction, where the dienophile is attached to the terminal carbon of the diene or carbon number 1. Okay. So it can lead to either cis ring junction or trans ring junction, depending on the presence or absence of the electron withdrawing group, and also the presence of chiral substituent in the tether can influence the stereochemical outcome of type 1 IMDA. It is also possible to have heteroatom present in the dienophile in intramolecular Diels-Alder reaction. Okay. So in the next lecture, we talk about type 2 intramolecular Diels-Alder reaction, where your dienophile is attached to the internal alkene of the diene or attached to the C2 carbon of the diene, and we will discuss subsequently more examples of type 2 intramolecular Diels-Alder reaction. Thank you.